In this session, we will see several concepts related to functions and variables. This will allow us to break down a big program in small pieces that could be saved in different files, and moreover, it will make possible to reuse the written code in several projects. When the first time we have talked about variables, we have illustrated them as labels attached to boxes. It is really a good example, and it is important in Python to start thinking about them as names bound to values. A name could be bound to any item in Python, immutable and mutable values, complex objects, or functions. Objects are stored in a global memory, a really big warehouse, while names are stored in a table that links names with objects. That's what we call the symbol table. We know that a simple assignment such as a equal 1 creates the object 1 if it does not already exist, and labels it under the name A. Moreover, for reasons of economy, the same object can be labeled with several variable names, as shown in the example. Let's see how the current example is internally stored in Python. Notice that I have made use of the keyword is instead of the operator double equal. Two objects could be equal but be different items. Let us create two lists with the same content. As they are mutable objects, Python creates two different instances, so if in the future the object labeled D is modified, it will not affect the object C. When an interpreter of Python is run, a new global symbol table is created, that is, a place where names are associated to things, boxes. Why is this so important? Well, each time we execute a function, a new table of symbols is created for the execution of that function. That led us to the important concept of local and global variables, and allow us to understand how the function parameters work. So let's go back to the definition of functions. At this point, we are going to follow the example exposed in the official Python page. In mathematics, the Fibonacci numbers are a sequence of integers characterized by the fact that every number after the first two is the sum of the two preceding ones. So let's write a function that prints the Fibonacci sequence up to a number passed as parameter. The keyword def introduces a function definition. It must be followed by the function name and the parenthesized list of formal parameters. A function definition introduces the function name in the current symbol table. The value of the function name has a type that is recognized by the interpreter as a user-defined function. So yes, a function in Python is like any other object of Python, and therefore the name of a function is only a label bound to it. It is immutable, and with its type it is possible to execute it in the same way that a list allows the use of square brackets to access the elements that are stored in them. This value can be assigned to another name, which can then also be used as a function. This serves as a general renaming mechanism. The first statement of the function body can optionally be a string literal. This string literal is the function's documentation string or docstring. For example, when defining the function fib, the object corresponding to the function is created, and a new entry in the global symbol table is added. When a new variable is used for referencing the same code, a new entry is added to the global symbol table. What it is really important is that the execution of a function introduces a new symbol table used for the local variables of the function. Imagine that the function parameters are local labels that are bound to the object that you place when the function call is executed. The actual parameters, arguments to a function call, are introduced in the local symbol table of the call function when it is called. Thus, arguments are passed using call by value, where the value is always an object reference, not the value of the object. When the function ends, the local symbol table is deleted. and the created objects are removed if no one is referencing them. Each time the function is executed, a new symbol table is created for it. More precisely, all variable assignments in a function store the value in the local symbol table, whereas variable references first look in the local symbol table, then in the local symbol tables of the enclosing functions, then in the global symbol table, and finally in the table of buildings names. When a function calls another function, a new local symbol table is created for that call. Thus, global variables cannot be directly assigned a value within a function unless named in a global statement, although they may be referenced. If you try to assign a value to a global variable not declared like that into the function, a new entry in the local symbol table will be created. As always, if objects are immutable, you cannot modify them, but if they are mutable, the object can be modified. Thus, arguments like lists or dictionaries, when modified by a function, are modified in the global scope too, but integer values or strings are not affected by the function execution. For example, the following function removes the ones that are included into a list and counts the number of ones that have been removed. As you can see, it is not possible to modify the parameter. As we have seen, when a new value is assigned to num, a new object is created and linked to the local level num. Thus, n does not change. Nevertheless, the content of the list is modified because the object is mutable. The return statement returns with a value from a function. A return without an expression argument returns none, and falling off the end of a function also returns none. It follows that every function in Python returns a value. Therefore, the use of the return statement is optional, as we can see in this first example. Writing the value none is normally suppressed by the interpreter, if it would be the only value writing. You can see it, if you really want to, using print. In the second example, a return without an expression is used to finish the function call execution. In Python, it's possible to return an object or a tuple of objects that allow us to return several values to the calling function. Let's see it by modifying the feed function. It is simple to write a function that returns a list of the numbers of the Fibonacci series, instead of printing it. At the end, when the sequence is completed, we return the list. The returned value can be used or referenced from the calling function, or as in our example, directly from the Python interpreter, which was the one that called the feed2 function. We can also modify this version in order to return more than one value, for example, the list and the number of numbers computed. For doing that, we can create a tuple with the set of items we want to return. We could then reference the tuple as a Python object, or, and this is quite interesting, we can assign independently each element of the tuple with a comma-separated list of variables. Okay, we will finish here the introduction to Python functions, but I recommend you to learn more about functions in the Python official site. But we have to move on and talk a little about modules and packages. As your program gets longer, it would be nice to have the possibility to split it into several files for easier maintenance. It would be also nice to be able to group functions and variables that have something in common in the same file or subset of files, making it easy to reuse that code in other programs. To support this, Python has a way to put definitions in a file and use them in a script, function, or an interactive instance of the interpreter. That files are called module. We will begin by creating a module with the following min and max functions. A module is a file containing Python definitions and statements, and the file name is the module name. So if we want to name it as the min-max module, we must create a text file called minmax.py. As we know, the suffix py is used to indicate that the file contains Python code. In any program where we want to use the functions min and max, it is enough to include the following line before. When a module named min-max is imported, the interpreter first searches for a built-in module with that name. If not found, it then searches for a file named minmax.py in a list of directories given by the variable sys.path. Sys.path is initiated from these locations. First, the directory containing the input script, the variable Python path, a list of directory names with the same syntax as the shell variable path, the installation dependent default. That's the reason of moving to the directory before running the Python interpreter in the example. Notice that we write from minmax, not from minmax.py. The file extension is not part of the module name. When you import a module for the first time, Python automatically creates a file called minmax.pyc. That file contains a version of your module easier to load in memory for Python, but absolutely unreadable for people. It is encoded in what we call binary format. If you delete the file, nothing serious will happen. Simply, Python will recreate it when you load the minmax.py module again from any program. When you import a module, the code is executed, and in the module symbol table, a variable name is created and initialized with the module name. But you can also run a Python module from the command line, as we have seen in the first session with the code in the module will also be executed, just as you imported it, but with the variable name set to the value main. That means that by adding this code at the end of your module, you can make the file usable as a script as well as an importable module, because the code that passes the command line only runs if the module is executed as the main file module. A module can contain executable statements as well as function definitions. These statements are intended to initialize the module. They are executed only the first time the module name is encountered in an important statement. They are also run if the file is executed as a script. Finally, each module has its own private symbol table, which is used as the global symbol table by all functions defined in the module. Thus, the author of a module can use global variables in the module without worrying about accidental clashes with a user's global variables. Packages are a way of structuring Python's module namespace by using dotted module names. For example, the module name rpimath.arithmetic designates a submodule named arithmetic in a package named rpimath. Suppose you want to design a collection of modules, a package, for some mathematical operations. There are a lot of math functions, so probably you will need to classify them in order to be able to maintain and work with them. Here is a possible structure for your package rpimath. We decide to classify our operations into arithmetic and trigonometric subsets. Well, Python uses the directory structure for it, so the package could be implemented as shown in the figure. Our min-max module have been included into the rpimath package and the arithmetic subpackage. Notice that all package directories include a init.py file. Those files are required to make Python treat the directories as containing packages. In the simplest case, init.py can just be an empty file, but it can also execute initialization code for the package, as you can see in the Python documentation. Users of the package can import individual modules from the package. For example, import rpimath.arithmetic.minmax. This loads the submodule rpimath.arithmetic.minmax and must be referenced with its full name. An alternative way of importing the submodule is from rpimath.arithmetic import minmax. This also loads the submodule and makes it available without its package prefix, so it can be used as follows. Yet another variation is to import the function or variable directly from rpamat.arithmetic.minmax import min max. Again, this loads the submodule, but this makes its functions min and max directly available. Note that when using from package import item, the item can be either a submodule or subpackage of the package, or some other name defined in the package like a function, class, or variable. The import statement first tests whether the item is defined in the package. If not, it assumes it is a module and attempts to load it. If it fails to find it, an import error exception is raised. Contrarily, when using syntax like import item.subitem.subitem, each item except for the last must be a package. Finally, a few words about PyP and the shell tool pip. Packages are especially important because they are easy to import and use, and Python comes with a lot of packages that can do almost anything. Pip is a modern, general-purpose installation tool for Python packages. Most often, it is useful to install it in your system Python. For example, there is a very famous package named NumPy that gives you a lot of mathematical functions. If you want to use it, you can retrieve the package very easily. You only have to write in a shell pip install NumPy. The pip tool will make the package accessible to your Python scripts or programs just by importing it on them with the import statement. I recommend you to check the Python official page for more information. Okay, with this session we finish the brief introduction to the Python programming language. As a summary, in this session we have here function definition and the concept of symbol table, how parameters work and the return statement, how to write modules, and finally, a brief introduction to Python packages.